Almost done? Anybody need a little more time? Done? Are you guys done? 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 Are you done? Good. Okay. Let's get started. So today is Friday, of course. Next week is holiday. Okay, we're not gonna teach lots of new stuff. We're just gonna review mostly, and however, it's some new stuff, but is related to multiplication. So what we're gonna cover today. So what was the goal of this class? The goal was to see how processor or CPU works and how you can design a processor. So we talk about abstract layers, starting from software or OS, compiler, and then ISA, and then microarchitecture, digital logic, circuit design, and physics. The part that related to this class is ISA and microarchitecture. We finished ISA. ISA was instruction set architecture. We talk about instruction set. We talk about addressing modes. We talk about registers in one computer. That was RISC-V. And also we talk about data type a little bit. But right now we are in microarchitecture design, but sometime we're going to come back to ISA and compare and, this kind of stuff. Like today, we are still designing microarchitecture, like a components of the computer. And last class, we started about ALU, arithmetic and logic unit. We said ALU is ALU actually considered part of the data path, is part of the data path. Generally, microarchitecture has two parts, data path and controller. And ALU is part of data paths. So it's actually data. What is data path? Data path is like connection of registers, ALU, multiplexers, memory, those things together, and makes everything ready when the clock coming, operation get done. Something like that. We had some examples last class about ALU data paths for doing multiplication. We're going to see them more today. That's like a basic of computer. You need to understand how this data path works. You're connecting all modules. These modules can be multiplexer, adder, or bus and registers. And of course, controller is also giving, making these control signals for all of these parts. And these control signals are very, very important because it's give kind of command to parts to what they do. For example, ALU can do so many things. But when, for example, controller send add message, so it means just to add or subtract or whatever. For registers too, registers also have some control signals. So controller makes those control signals and waiting for signal for clock cycle to comes to finish the job. Last class also we talked very important part, important topic related to critical path. We said, okay, in computer, we have a critical path, that this critical path is a slowest things that we are doing in our computer, and we are defining your clock cycle based on this critical path. So also we We talked about multiplier. We talked about adder. We said sometimes we can do with design or engineer or components more advanced to make it faster. Like we saw that in um, Ripple adder, that we used um, actually extra circuits to um, actually find the carry earlier. We call that look ahead carry circuit. Uh, and what else we learned last class? Also, we talked about um, multiplier that we're going to continue today and see how we can make the multiplier faster. So we're going to talk about that today. Also, we're going to see how we can use parallelism to do things parallel instead of having, for example, one adder and multiple time use it. Maybe we use multiple adder or multiple ILU to do some operations faster. I wanted to talk about divider too, but I'm not going to talk about that today. But it's part of your assignment. We can see that in your assignment. Okay, so this is what we're going to cover today. So last class, we talked about multiplier. So we already know how to do multiplication using, in decimal numbers. When you do multiplication, multiplication is like adding. So we do 1 digit by 1 digit and add them up. So in multiplier, if we have, for example, n digits, so when multiply them together, they might need 2n space for that. In binary also is the same. In binary is much easier because in binary we just have 0 and 1, and 0 multiplied by anything gonna be 0, and multiplying 1 by anything is gonna be just whatever was that. It's not gonna change anything. So it's gonna be very simple. So it means these partial products are not something new. They might be multiplicand. We call multiplicand, we can use capital M for multiplicand, and or 0. Okay, the reason is that because it's binary. These multipliers, they just have 0 and 1. If it's 0, this partial product all gonna get 0. And if it's 1, this partial product gonna be exactly multiplicand or capital M. Okay, so that makes it simple. So what else we learned last class? We also learned how we can design an algorithm to do that that binary multiplication using like a modules like registers, ILU, and controller. So if you look at this flow chart, you can see we are making decision based on multiplier least significant bit. So least significant bit, LSB, of multiplier deciding what we do. Because, for example, if you have 1, 0, 1, 0 as a multiplicand and 0, 1, 1, 0 as a multiplier, the addition was like that. So first we are testing a less significant bit of multi, because it's 0, we're not going to do anything. So it means like we are just putting 0 here. And if it's 1, we are adding multiplicand, because 1 multiply with that is going to be multiplicand. We just put multiplicand here and add them and then shift. So in this algorithm, so you just need to shift multiplicand to the left. So it means you're, as you can see, we are shifting that to the left. So this is multiplicand that we shift that left, is like putting another 0 here and then add them up. So exactly what happening multiplication by hand, we write the algorithm to do that. So again, another one, it's going to be 0, 1, 0, 1, 3, 0, and another one, it's going to be 0, 0, 0, 0, and then add them up, it's going to be 0. I think I made mistake. I made mistake. 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So it's going to be 0, 0, 1, 1, 1, 1. Okay, 1, 2, 3, 4. Oh, yeah. Anyway, I think I didn't write that in a proper. So anyway, this is the algorithm. So how we can do that with this data path? This is the data path that I'm talking about. If you have some modules like multiplier, ILU, the registers, ILU, and controller, this connection of these parts, these modules makes a data path. It's showing how data passing between these modules. But we didn't show the clock here, but you also have clock here. That's the important part. Clock is playing very important role in this data path because, and clock is just connected to sequential circuits like registers. A controller is not sequential, and ILU is not also sequential. Last class, we saw how this works. So what you are doing, the product at the beginning is 0. I just consider 4 bits here, but it can be 64. As you can see, we need to, if we do this kind of design, we need to have 2 times of n. If, for example, it's 4-bit, you need to consider 8-bit multiplicand registers, like here, for example, 1, 0, 1, 0. The rest is 0. Here is product is also 128 bits. This is 128 bits. Product is at the beginning 0, but is 8 bits in this case because I considered 4 to make it simpler to show. And multiplier is 64. So multiplier here is 4, 0, 1, 1, 0. So if you ask me why we use multiplicand 128, the reason is that we need to shift that every time to simulate what's happening in real multiplication, like by hand multiplication. So as you can see, when we are shifting to the left, we just put enter, we just put 0 here. So this register, it just has this 64, but the rest are zeros. We are kind of wasting registers in this. Same things happening in this as well. Same thing that happening anytime we actually, in this too as well, in multiplier as well. We don't need to, because anytime you shift that 1 bit this side, we are entering an 1, 0 here, and it's going to get 0 at the end. However, this is simpler to just find these decisions. See, are we done or not? Because we're just going to check this multiplier. If it's 0, we are done and we can go up. But anyway, this is not optimal method for design. So another design exists that is more optimal in a sense that you don't need to use 128 byte registers for multiplicand, and you don't need a multiplier at all. Even ILU is just 64-bit ILU. The other one was 128-bit. So let's see how this works. So what we can do is that we are using another register. This register is 129. I'm gonna tell you why we have one extra bit here. But anyway, this can be used for two sides, product and multiplier. And instead of shifting multiplicand to the left, we are is the same way to just shift product to the right. If you write the algorithm by hand, you can see, oh, they are like equal. So let see how. Okay, again, let I write this multiplication. Okay, this is 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. When we add them, 0, 0, 1, 1, 1, 1, 0. And as you can see, this is 8 bits. Because you have two 4 bits, when we multiply them, to fit that, you need 2n space to put all of it there without problem. Okay, so what's happening here? In the previous algorithm, we were shifting multiplicand. This was multiplicand to this side. But what about is same way to just because we are product is this 2 is product, and then that with this is a product. Product is adding. What is product? Product is equal to previous product plus m. M is multiplicand, capital M, and lowercase m is multiplier. Okay, so let's see how this is happening in an example. Okay, so as you can see, this register has two parts and playing two roles. It's just for adding and also for shifting as well. As you can see, it has two controllers, one for write and one for shift right. Okay, and this is 129 bits. It means one extra, that this is a carry. The reason is when you are adding a previous product with the multiplicand, sometime because you are adding two n-bit registers, is going to be n plus 1. So you need to put this carry here. And this carry is important. Why is important? Because when you shift that to right, that's not going to say carry anymore. So that's why we need to hold it. We need to keep it somewhere to use it for later. We can't just not use that and don't consider that. So that's the carry bit. The rest is just a product, and this is multiplier. Okay, let's do example. In this example, let's change the color. In this example, product was 0 at the beginning. Okay, that's 0. I just consider 4 bits. And multiplier was 0, 1, 1, 0. Okay, let's see what's happening. And multiplicand is 1010. Okay, what happening here? Controller, and this is the clock cycle. No, it's not writing here. Good. We're gonna put it here. This is clock cycle. Okay. Right now we are at the beginning. So what's happening? The controller easily, without any clock, can check multiplier least significant bit. Least significant bit is 0. So when it's 0, it means we're not supposed to add based off the algorithm. So we're not supposed to add. What we need to shift, shift is 1, right is not, add is 0 2. Add 0 means we're not gonna add, okay? So 0 means we're not gonna write, we're not gonna add. 1 means we're gonna shift. Okay, so this is happening in here. So if we put the control signals here from top to down, we have 0 1 0. This is control signal. Control signals. These control signals can be created by controller. Here we have just a small controller, but in real computer, we have a control unit to make all of these control signals. And the time to create the control signals is between clocks. So it makes that ready. And when this get ready, the modules, the parts that are combinational, they can do their job, because combinational doesn't need any clock to do that. So this ILU can start working. But because it's 0, it's not going to do anything. But if it was 1, it could start doing adding. And when there is a connection from this product to up, it means in this bus, this is a bus. Here is 4 bits, but that in real is 64 bit. Here is, I just consider 4 bit in this example. So it means in the bus already we have 0 0 0 0. So it's ready for ILU to do operation, but it's not doing anything. Why? Because it's 0. Because the controller tell ILU don't do anything. Okay, so clock coming. The rising edge coming. When the clock coming, sequential parts start acting. So this register is not normally register. It's a module by itself. Because it has 2 parts, shift and write. So it's not a normal register. It's a very advanced register. So what it's gonna do is it's gonna do 2 things, but not at the same time. It's not possible to do at the same time. Some part of that can be done sequentially. Some part of that is, again, combinational. Like, for example, we can, as far as actually we need to know, we don't need to design this right now. We don't want to make it complex. But what's going to happen, we do the write first and then shift. So this is, if we consider this order, we can understand it easier. But all that happen in just 1 clock. Okay, but this was 0, nothing happened. The only thing that happening is shift. So when the clock coming, this register gonna change. How is gonna change? We're gonna shift it, shift to right. So when shift to right, this bit gonna get off, and another bit gonna come here, okay? And another bit gonna come from here, or maybe this carry gonna go inside, okay? So this 2 red means we took 1 from this product inside the new multiplier, okay? And we shifted in from most significant in 1 0. Okay, so that was this is the new value. Controller still start working. We are in this part. Controller start working. A controller checking and say, oh, there is 1 as a least significant bit. So it's going to make new um, control signals. This is one. So the control signal that is going to make, because it's one, we need to write, we need to shift. We always need to shift, but sometimes we need to write or add or not. But here we need to add because it's one. Okay. So if LSB, least significant bit, is one, we need to do shift, we need to do write, and we need to do add based on the algorithm. And if it's zero, we just shift, nothing else, just shift. Okay, so considering this algorithm right now, it's one, so we're gonna do write, shift, and add. Now, when this ILU input get one, it means we need to do add. What is the product? What is the input? Zero. It still is zero. It didn't change. So we're gonna add zero with the multiplicand that was, we didn't change multiplicand, we did not change multiplicand anymore. So we just added with that. So the result gonna be 0, 1, 0, 1. Okay? And then we need to do shift and write. First we do write, because clock coming, we are right now here. Clock coming, so we need to do write. We do write here. And this part is still same as before. And then we shift. When we shift, this another one gonna get disappeared from here, and another zero gonna come here, and this gonna get disappeared, 1 0 gonna come here. Okay, so this is the new values inside the product and inside the multiplier. Okay, that's good. So this is the control signal. Again, we are controllers start reading least significant bit. It still is one. So still is one is going to make same signals as before. It's going to make same signals as before. Okay, but right now the input for adder is this, is changed. It's not zero anymore, and the adder can work without clock. Adder start adding these two together, so the result gonna be 1, 1, 1, 1, and waiting for clock. So the clock coming, we need to write that inside the product. We're gonna write that inside the product, 1, 1, 1, 1, and then shift. When we do shift, this gonna get 0. This gonna get 0, 0, 0, 1, 1, 1 from product gonna come here, and another 0 gonna come from the end inside. Okay, so that's a new one. Okay, what is the new LSB? 0. Because if it's 0 coming, we don't need to add, we just need to shift. So the new control signals is this. So it means we don't need to add, so we don't do anything. And when the clock coming, we just shift. And when we shift, and at the same time, this controller counting the number. And right now, the counter is 4, so we are done. After shift, we are done. The result is this. And as you can see, it's the same as here. So like this is the 4 bits. That's the 4 bits. So this is how working. This is very good design because we are using 1 register and 2 input. So I want to show you, I want to actually, in this example, you see how engineers can think differently to like a simple problems to make it more optimized. We are not adding a speed to this design, but we are decreasing the complexity and make the system less components. So if it's going to be actually much cheaper, it's almost half registers if you want to consider the number of registers, because this ILU instead of 128 is just 64. This is half. We don't have the other one too, so it's almost half. And this design is optimized design. But in terms of clock, it's still how many clock we need to multiply n-bit registers in this example. Imagine each ILU doing, for example, 1 cycle. If each ILU doing 1 cycle, how many cycle we need to multiply 2 n-bit registers? You tell me. That was the question of the quiz, isn't it? What you answered. But that was for the other one, but they are the same. It wasn't the question for your assignment, for your quiz? It was. It was one of the questions. I asked you how many cycle we need if we have n-bit registers. Oh, do you remember that?
For the sequential one, it
yeah,
was n cycles.
Right? N cycle. Yeah. This is sequential too.
Yeah, sorry.
Yeah, it's just we need n cycle. Yeah, this is sequential too. We didn't do parallel. We're going to see parallel soon, but this still is sequential. So let's see how we can do that faster. So this is not faster. This is optimized, but not faster. But if you want to make it faster, we need to make it parallel. The parallel design is a little complex. So the idea is, instead of having, for example, n time adding, what about we use n adder and put them like a series? We can do, because in this previous picture, as you can see here, so we have these partial products. What about we make these partial products separately and put them, instead of add them in a sequence, because this sequential is just doing this add 4 times. This is the 4 for this example, but in 64 bits, it's going to be 64 of this. So what about, instead of having 4 times looping in this to add them together, we use 4 adder. So this going to make a new design that is a parallel design, that is this one. The idea behind this is coming from this formula. We can say a product in multiplication is adding mi. M is for multiplier. Capital M is a multiplicand, and shift can be done with 2 power I. Okay, let's do example to understand what this is saying. So imagine this, we are multiplying. M is 10112. 2 means binary. And a multiplier is 1101, again 2. So to do that, we need 2. This structure is a tree structure. And doesn't need even adder bits, the 128 bits. It's 64 bits. This is very optimal. Very optimal. It's very hard to understand. And the people that designed that, they were very smart, actually. So let's see, when I run it for these values, these 4-bit values, you might understand it easier. So what we are doing, but the idea is this. The idea coming from this. What is that? The product, the final product, is sum of these partial product. They are partial product. If you remember in that example, those partial products coming from the bits of multiplicands, these bits multiply with them. It can be 0 or 1. M is not changing. M is always that. And 2 power I means shifting to a left. Multiplication by 2, each multiplication by 2 is shifting 1 bit. If you have 2 bit, I is 2, so you are actually multiplying by 4. Okay, so as you can see in this picture, we have M0 multiplied with multiplicand, M1, M2, M3. Whatever you have, here we have 64. In this example, we just have 4. So I'm just going to write 2 adder, actually. And in this adder, you have M0. Okay, what is M0? M0 is 1, M1 is 0, and M3 is 1. Okay? So M0 multiplied by M, M1 multiplied by M, M2 multiplied by M, M3 multiplied by M. So let multiply that. So M0 is 1. So the result is going to be 1, 0, 1, 1. The result of this is going to be 0. Okay? But not just 0. We okay, let's first multiply and then shift them. The result of this is going to be 1, 1, 0, 1. The result of this is going to be 0, 1, 1, 0. Okay? So, and then we shift them. The first one is we shift 0. So we are not actually shifting. We are not shifting because I is 0, so is 1. For this one, we are shifting. When we are shifting, 1 bit coming in. When we are shifting here, 2 bits coming in. And this one, 3 bits coming in because I is 3. Okay? So the new values are that. And then what's going to happen? We took, as you can see here, we took least significant bit and most significant bit out. That's the trick part. So we take this part out. So 1 coming out and 0 coming out from here too. So this let us to make the addition instead of 2 4 bits, 1 3 bits, 1 4 bits. And it's going to make it easier to not make carry. So we take already one of them out. We don't need to. This is going to help us to, instead of having 128 bits adder, we just do it with 64-bit adders, or in this example, just 4-bit adders. Okay, so you need to do it at home to understand what I'm talking about. So if we take that out, so the new number going to be this. We add them together, the result's going to be this. And here also, if we add them together, the result's going to be 0, 0, 0, 1. What we are adding, let I do another, oh, what I did. Let me go back. No. Oh. Okay, sorry, I need to draw again. Anyway, so let's write in this. Yeah, but I can draw it again. That's fine. Very fast. Okay, so here we have 1, 1, 0, 1. Here we have 0, 0, 0, 0. Here we have 1, 1, 0, 1. Here we have actually 1, 1, 0, 1. We take this out. We take this out. Oh, we also have 2 bits here. We have 2 bits here, or yeah, we have. Oh, actually, let this one. This is okay, and this has 1. Okay, and when we add them together, it's going to be 1, 0, and 0, 1 here. There is 1, 0, 0, 0. Okay, so for the next adder, we don't do shift anymore. No shift, because you know what we are doing? We are simulating that a subproducts or partial products together. We are in that example, if you remember, the partial products were this one. However, here it's changing. So I don't know if we have time. We don't have time. Anyway, so this is happening here. We can explain that later more. But uh, here, what we have, we take one out. So the result is 1010. Here the result is 0001. We take another bit out. Here we took one out. Here we took one out. Here we take another out. Here we take another out. And this is going to be just adding 3 bits. These 3 bits. This and this. When we add them together, the result is going to be this. So the overall going to be 10001111. This is the final answer. Okay, so I explained that fast, but you can understand it right now if you go home. If you look at this picture in the book, there is not enough information to how it works, but I think you got the idea what's happening. Whatever we are doing in partial product, we make them here, and we want to make a structure like a tree. In this case, if I ask you how many cycle we need in this case, if each adder do just one cycle, so you need to count this number of layers in this tree. What's the number of layers in this tree if we have n bit as like registers are n bit? So how many layers we gonna have? So here we have n. So here we have log of n2. So if we count this, it's going to be, instead of have n layer, we have log of n base 2. So this is much faster than the other one. Okay, there is no time. So we just have some instructions just for multiplication RISC-V. But the point is, for multiplication, because result is 128, we need to have 2 instruction, one for lower register, one for upper registers. So we can have another example next class. Okay, so hope you have a good holiday and rest enough, and see you the week after your spring break.
This is the first time seeing it.